Hi guys, and welcome back to Chemistry 1032 Blended Class Instructional Video. I am your professor, Dr. Russell Betts, and I'll be talking to you through this presentation. This is the last video for Chapter 10, at least I hope it's the last video. And we'll be talking about reactions of acids and bases. So no sense wasting time, let's get to it. Reactions of acids and bases. We're going to talk primarily about carbonates and bicarbonates because they're the most important ones that you kind of have to know. They're really kind of cool. In fact, most of you have used them and probably didn't even understand what you were doing because, you just added it. If you ever bake cookies or cakes, you've used chemical leaveners, sodium carbonate. You probably know it as baking soda. It's a very, very nice chemical leavener. It makes your cookies and cakes and fudge, sorry, not fudge, but brownies and all the other kind of really delicious things. It makes them rise and become fluffy. Now, how does it do that? Well, carbonates, CO3s, and bicarbonate, HCO3s, react with acid. These are acids. And when they do that, they generate carbon dioxide. Okay? These are called gas-forming reactions. They form carbon dioxide. Now, excuse me. That's kind of important, right? Because when you make carbon dioxide, as you're baking, say, a cookie, you bake it in the oven, and the baking soda comes into contact with acid in the food, and it creates CO2 bubbles. And these bubbles are what make the fluffiness in cookies, cakes, muffins, and all these other kind of delicious things people eat. Okay? Now, when you do this kind of reaction, you also form a little bit of salt, a little bit of sodium chloride, and additional water. Okay? So you always get CO2, some kind of salt, and water when you react an acid with a carbonate or a bicarbonate. What I need you to know here is that when carbonates or bicarbonates react with acids, you always get CO2. In fact, if you took calcium carbonate, which is eggshells are made of calcium carbonate, you could actually put that egg, raw if you want to, into a glass of vinegar. Vinegar is an acid. And within probably a few hours, you're going to start seeing bubbles forming on the outside of the shell where the vinegar acid reacts with the carbonate in the shell, making CO2. And if you leave the egg in that glass long enough, I'm not sure how long it takes, probably a couple days, maybe a week, the shell will actually dissolve, leaving you with the egg surrounded by that membrane. You've all seen the membrane when you crack an egg. There's a membrane that coats the inside of the shell. You're left with that membrane and the egg's inside of it. Now, I wouldn't eat the egg if I were you. Probably tastes nasty. It could be rotten by that point too. But you can certainly dissolve the shell off, and it's kind of cool. Kids like it. All right, the other kind of reaction you need to know for acids and bases is called neutralization. Essentially, when you add an acid to a base, you get neutralization. They react together, and they always form a salt, and they always form water. Now, neutralization reactions are important because whenever you have some kind of stomach indigestion where you get some acid reflux going on, the acid in your stomach is kind of gurgling up, so you got too much of it, and you got too much acid production. You take some antacids, right? Oops, sorry, one more slide. You take some antacids, Tums, Rolaids, all these things, and they neutralize your stomach acid. They don't neutralize all of it, of course, just some of it, just enough to knock it down a little bit so that you don't have such bad acid reflux. So when you're at home and you have your Rolaids or Tums or whatever, look at the label, and you're probably going to see these kind of things: magnesium hydroxides, aluminum hydroxides, probably not sodium hydroxide, but calcium hydroxide probably you'll see. These are all bases, right? And they all react with the acid in our stomach to help tamper down any excess stomach acid we may have. All right, that leads us to this. Buffer. Buffers are important. Buffers are extremely important. Write this down. The title, circle it, underline it, stars all around it. Very, very important, okay? Buffers. Now, let's take a look at a non-buffered solution. Non-buffered water. If I have a beaker filled with non-buffered water and it's at pH 7, neutral water, if I add acid, the pH is going to drop dramatically. It's going to plummet. If I add base, the pH is going to increase dramatically. It's going to skyrocket. Why is this? Because water is not what they call buffered. Now, what does a buffer do? A buffer solution. A buffer solution will maintain the pH. In other words, adding acid or base, the buffer will maintain the pH. Now, here's an example. Here we have our buffered solution. The pH is at 7. If we add acid, the pH drops to 6.9, essentially the same. Slightly more acidic, but essentially the same. If we add base to our buffer, it goes from 7 to 7.1. Still more basic, but only slightly more basic, not dramatic like you saw up here. This is dramatic, very big shifts in pH. Down here, not quite so dramatic, not a big deal, right? Now, how does that work? Well, it resists the change in pH from the addition of acid or base. Now remember, when you eat food or you absorb things, sometimes you absorb hydronium, sometimes you absorb hydroxide from foods, and like some stuff your cells will do, right? And your blood has a buffered system in it that maintains your pH at 7.4, all right? Now how does that work? Let's dive a little deeper into this. Your blood and a lot of things in your body are buffered. Why? Well, they want to resist the change in pH, okay? From whatever's going on. They want to resist any change in pH. Now, a buffered solution requires that you have a weak acid and its conjugate base. A weak acid and its conjugate base, okay? Now, they say here it has equal concentrations of the weak acid and its salt. When it says salt, think conjugate base. When it says salt, think conjugate base, okay? So that's a buffer. A weak acid can make a buffer as long as you have the weak acid and its conjugate base in solution. Strong acids can't make buffers, all right? It has to be a weak acid and its conjugate base. All right, so here we have a nice equilibrium. We have this carbonic acid and carbonate in solution. Now, this is a buffering solution, okay? How do I know that? Well, first of all, it's a weak acid and its conjugate base, and it's an equilibrium. Now, remember Le Chatelier's principle. Now, I didn't teach you that for nothing. It's important. Le Chatelier's principle says, if I add something to the right, the equilibrium will shift to the left, right? That's Le Chatelier's principle. If I add something to the right, the equilibrium will shift to the left. Now, what happens if I add things to the right? Or sorry, the left, excuse me. What happens if I add things to the left? The equilibrium will shift to the right. Is that not true? If you don't remember that, go rewatch that video on Le Chatelier's principle. So now what if I add, some of this. The equilibrium will shift that way, correct? Are you with me? So in a buffered system, Le Chatelier's principle is still working. Add a little bit to the left, equilibrium shifts to the right. Add a little to the right, equilibrium shifts to the left. Okay? That's what's happening in a buffered system. Now, here we go. Here's the nice schematic of it. So now here we have our acetic acid in solution. We add base to that. It's going to shift to the right. It's going to shift to the right. We know that's going to happen. Okay? Now, let me go back one sec. Here we have an equal amount of conjugate base and weak acid. So if we do this, we add base to this, we know that this concentration is going to go down. And in fact, it did. But what also happens is the concentration of conjugate base goes up. Okay? So the acid concentration goes down, the base concentration goes up. Acid concentration goes down, base concentration goes up. Now, what if we have this reaction going on? We have acid being added to our equilibrium. That means the ion, the negative ion, is going to react. It's going to produce the acid and water. So notice, if we have this equilibrium over here, so this is an equilibrium with that. Remember, they're in equilibrium. You add acid. The concentration of the acid on the left is going to go up, and the concentration of the base is going to go down because the base is reacting with the acid. Okay, so that's so far so good, right? That's if you add, and to an equilibrium, if you add base, the concentration of acid goes down. If you add acid, the concentration of base goes down. Okay, so now here's a review. We have this thing here and this here, a weak acid base solution. If we add OH, so we go this way, the acid, original weak acid concentration goes down, the weak base goes up. If we add acid, the concentration of acid goes up, the weak base goes down, or stays the same, in fact. Okay? So then remember that. This is very, very important. We have a weak acid. Oops, sorry. Let me clean that up a little bit. We have a weak acid. If we add base, the concentration of acid will go down. Concentration of the conjugate base will go up. If we add acid, then this is going to react. This concentration will go up. This concentration will go down. Okay? It's important. One more time. Let me clean this up. We'll go over it again. Remember, this is all Le Chatelier's principle. There we go. Clean that up. Do it again. We have an equal concentration of this and this. Excuse me, I have a little tickle in my nose. Okay. Now, we're going to react. We're going to add acid. This is acid. The acid will react with this. This is a base, but remember, this is a base, right? These two things, this thing here and that thing there, are going to react. When they react, this is going to get consumed. So this concentration is going to go down. Okay? But when this thing here and this thing here react, they're going to make this. Okay, that's what they're making when they react. So the concentration of the weak acid will increase, the concentration of the weak base will decrease. Okay? Now, let's try it again. Let's clean this up a little bit. Let's go the opposite direction. Now we're going to add base to this. Okay? If we're adding base, the acid will react. When the acid reacts, this concentration will go down, but when this thing here reacts with that thing there, it makes this. So this concentration will go up. And that's what you see. The base goes up, the acid goes down. So far, so good. That's what's happening. I know this is weird, and I know you don't like it. You're going to have to. Oops. Thought I had another slide there. Okay. So this is how buffers work, right? It helps to maintain the pH by when you react with a little bit of acid, you actually are making the weak acid, which is in equilibrium with its weak base. Okay, that's how these things kind of try to help maintain the pH. I get it, buffers are hard to understand, but please try. Remember, when you add base to an acid, to a buffered system, the conjugate base will react, the acid will react with it, neutralizing it. If you add acid to a buffered system, the conjugate base will react with it, neutralizing it. All right? That's how these things work. And the equilibrium gets reestablished by the weak acid and the weak base, and they maintain the pH. So the buffered system has a weak acid and a weak base together. If you add acid to it, the weak base will react with it, maintaining the pH. If you add base, the weak acid will react with it, maintaining the pH. I know it's weird, guys, and I know a lot of you aren't liking what I'm saying. I'm sorry. You still have to learn it, okay? Read it in your book. It's really not hard. One more time. Let's go over it and we'll end the video. You have a buffered system. You have equal concentrations of weak acid and weak base. So imagine that in your mind. You have an equal concentration of the weak acid and the weak base. Now let's imagine that I add strong acid to that. So you just put some strong acid in that solution. The weak base will immediately consume the strong acid. Because it's an acid-base reaction, they'll just react with it. And that will neutralize that strong acid that you just added. Okay? So it's like the strong acid was never there. Now let's imagine again you have equal concentrations of acid and base, weak acid, weak base, and I add base. You just dump some base in there. The acid, the weak acid, will immediately consume it. They'll just react together, maintaining the pH. Okay? I get it. Buffers are hard. You don't like it. If I were you, read it in your book. Watch some different videos, but be careful with the videos if you're going to go to the internet to find other people. Buffers are more complicated than this, a lot more. You might find yourself going down a rabbit hole that's more appropriate for a general chemistry student, not an allied health chemistry student. So be careful which way you go. My advice, read your book. Ask me, we'll go over it. It's really not hard, but it is fundamental. All right? Now with that, that is the end of chapter 10, guys. I know buffers are weird. I get it. I get that they're hard. I get that you don't like it. Physiology people tell me you need to know it. Microbiology tells me you need to know it. Nursing school is going to want you to know it. Learn it. Learn the idea of it. Now, they're more complicated than this. I promise you that they're more complicated. But this is what you need to know. And this will help you understand physiology. It really will. I've talked to numerous physiology students, and they kind of tell me the same thing. Like, they wish they had known this before they took physiology. So please do your best to learn it. And come on by and visit me if you have trouble with any of this stuff. I'm always available. Go see the tutors, see what they can say, and try to figure it out with them. But either way, don't sit back on it. Just let it, let it marinate in your mind. Try to figure it out. Try to think logically through it. I think you can do it. All right? Now with that, I want to wish you good luck, good chemistry, and I will see you in class.